So we're ready at this point in the semester to talk about higher order differential equations. And what we're going to do is we're going to start with second order differential equations, and then we'll generalize from there. And so in general, a second order ordinary differential equation, or ODE, is going to be some equation of the form capital F. It's going to be a function of x. We're thinking of y as a function of x, y prime, and y double prime. So it's going to have four inputs. So a variable x, and then the function y, and then its derivative y prime, and second derivative y double prime equals 0. So that in general is what all of the second order differential equations are going to look like. So this includes things like y double prime plus say 4x y squared plus y equals 7. So that's the type of thing that we're going to look at. What makes it second order is that the highest derivative that you see in the equation is y double prime, right? It's the second derivative, so that's why it's second order. Just to make that a little bit more salient, let's change this to 4xy to the fifth. So this is still a second order ODE because the order of the differential equation is determined by the highest derivative that we have here. And so what we're going to do is we're going to start with second order ODEs, and then we'll generalize from there. Second order ODEs is what we're going to spend a considerable amount of time on in this course. And what we're going to do to start with is we're going to talk about what are called linear. There's a lot of words that go here. Linear second order ODEs. And a linear second order ODE is a differential equation that can be manipulated to be of the form y double prime plus p of xy prime plus q of xy equals, say, r of x. Okay, and so this is linear in the sense that all of the y's are there to the first power. So you have y, y prime, y double prime. Those are all to the first power. Nothing's being multiplied. If you were to have something like y times y double prime, then it wouldn't be linear anymore. So linear specifically refers to differential equations of this form. And actually, the first thing that we're going to do is we're going to look at what happens when this right side, our right side here, r of x, when that's 0. And so these are called linear second order homogeneous or homogeneous ODEs. And that's going to be what we spend a lot of time on. And actually, there's one last simplification that we're going to make. And then the last thing that we're going to simplify, which is actually a subset of the linear second order homogeneous ODEs, is we're going to first tackle what happens when p of x and q of x are constant functions. And it turns out that when those are constant functions, we can do these explicitly in detail. We can solve everything there is to know about them. So actually, the first thing that we're going to do is we're going to solve linear second order, sorry, this gets a little bit ridiculous, linear second order homogeneous ODEs with constant coefficients. Okay, and those we can solve explicitly. Okay, so that would be something like if we were to have y double prime minus 5y prime plus 4y equals 0, something like that. Okay, so that's where we're going to start. And the way that we're going to handle this is we're going to think about what are the functions whose derivatives are really close to the functions themselves, because this is exactly the type of thing that we're going to look at when we see y double prime. So when we see a second order linear homogeneous ODE with constant coefficients, these are all going to turn out to be some sort of exponential type functions, and I'll explain exactly what I mean by that in a second. But exponentials are the functions whose derivatives are very closely related to themselves. So for example, we can check that y equals e to the x is going to be a solution here, because if we were to compute y prime and y double prime, that's of course still just e to the x, right? So we know that y prime is e to the x, y double prime is e to the x. And so all of that together says that if we have e to the x minus 5e to the x plus 4e to the x, that's 0. And of course, that is 0 for all x. Whenever at this point, and this is going to be a subtlety, we're not trying to figure out what are the x's that are going to make this 0. So sometimes in algebra class, you look at things like, just to make up an example, x squared minus 3x plus 12, I'm just making up an example, equals 0. Okay, that doesn't have real roots. It doesn't matter. If you want it to have real roots, make it plus 2. That's not what we're doing here. What we're doing when we say that this is equal to 0 is we're thinking of this right side as being the 0 polynomial. So we want to know what are the functions where this is always 0. Okay, so something like e to the x, no matter what x is, that left side is going to be 0. So I just want to emphasize that's a slight subtle difference there. It turns out if you wanted to find the other solution, you can check that e to the y equals e to the 4x is also a solution, because the second derivative will be 16 e to the 4x minus 5 times, so the first derivative would be 4e to the 4x, and then y itself is 4e to the 4x. And you can check that that'll also be 0 because you get 16 minus 20 plus 4. So you get 0 e to the 4x, which is 0. And it turns out that those are the only solutions in a certain sense. But actually, there's infinitely many solutions in another sense. So another thing that happens is that if you take a constant, so something like 7 e to the 4x, that's also going to be a solution if you think about it, because you can take that 7, and the 7 gets factored out whenever you're taking derivatives. So you can factor the 7 out of here, factor 7 out of here, factor 7 out of here, and then divide both sides by 7, and you still get a solution. So, and in fact, there's nothing special about the number 7. Any constant times e to the 4x will give us a solution. One other thing to check is that if you add the two solutions, you get another solution. So you can also check that if you have y equals e to the x plus e to the 4x, that's also going to be a solution, because what's the first derivative? Well, y prime is e to the x plus 4e to the 4x, and y double prime is e to the x plus 16e to the 4x. And what you can do is you can look at y double prime minus 5y prime plus 4y equals 0, and that's going to be e to the x plus 16e to the 4x, minus, I better put this on a new line because I'm going to run out of room. So that implies that e to the x plus 16e to the 4x minus 5 times y prime, which is e to the x plus 4e to the 4x, plus 4y, which is 4 times e to the 4x plus e to the 4x. Sorry, 4 times e to the x plus e to the 4x. We want that to be equal to 0, and let's just check it. And of course, this will work, because what you can do is you can just get the e to the x terms all by themselves. We know that those add up to 0. Then you can look at the e to the 4x terms, look at those isolated from everything else. Those add up to 0. And of course, you're going to end up with 0 equals 0. So it's going to work out just fine. So it turns out that whenever you find any two solutions, what you can do if you want to get infinitely many solutions is you can multiply any of the solutions by a constant. Okay, so you can multiply any solution by a constant. You can add any of the two solutions. So in general, the what's called the let me say it this way, the general solution. So the general solution to the differential equation y double prime plus what was it? Y double prime minus 5y prime plus 4y equals 0. So the general solution is going to be c1 e to the x plus c2 e to the 4x. Okay, and so this is a general principle known in differential equations that's actually true for any homogeneous linear ODE. It turns out that if you have any two solutions, you can add them together. If you have any solution, you can multiply it by a constant. And then this gives you what's called a linear combination, where you take a constant times one plus a constant times the other of all the solutions, and then this will describe the general solution to the differential equation. Now, what I mean when there's infinitely many solutions is that pick whatever, you have infinitely many values for these constants. They could be, say, pi and negative 40. They can be whatever you want. you have infinitely many values there. But on the other hand, the solution to the differential equation are only these functions. There's no other functions that'll work. So in that case, there's really only one general solution to the differential equation. So what I want to do at this point is let's just write down, I've basically proved the two statements already, but let's just write down the two statements that are going to be true about linear differential equations. And there's actually nothing special about second order linear differential equations either. If this was a third order differential equation and you had three solutions, then you could do this and add all three of them together and have three constants. Notice that this is a second order differential equation and we have two constants like we would expect. Okay, so if you have to anti-differentiate twice, you should have two general constants there. So let's go ahead and let's write down this rule in general. So I'll call this a proposition. And actually, I'm just going to write this down for second order ODEs, but this extends to nth order ODEs where n is as big as you want. So consider the differential equation. This has to be linear and homogeneous. So y double prime plus p of xy plus q of x plus p of xy prime plus q of xy equals 0. If y1 and y2 are solutions to this differential equation, then so is the general quantity c1y1 plus c2y2. Now, depending on what p and q are, if you have, depending on what those functions p of x and q of x are, that can change how many solutions you're going to get to the differential equation. If p and q are constants, you always have two solutions up to multiplicity. So maybe you have, I'll explain what I mean a little bit more, but you'll always have two solutions in a certain sense. So that's really all I wanted to say about second order linear ODEs in general. And then what we're going to do now is we're going to go through and we're going to go ahead and solve differential equations of this form.